Hello. So general solutions for trig equations. So find the general solution for each of the following. Well, general solutions are like the list of all the solutions. So if we had a COS graph, for example, and I just sort of drew in that COS graph, normally the period's 2 pi, but we know it goes on forever and ever. So if we were sketching in our COS graph, look like that, and then like that. And obviously that goes on. And we said, well, where does that equal 0.5? So there's 0.5. You can see there's one solution, there's another, there's another, there's another, and that goes on for forever. So how can we come up with all those solutions? And that's what we call general solutions. So start like normal. So cos x equals, I'm going to make it a half. So x equals cos to the minus 1 of a half. So we know from our special triangle, 2, 1, root 3, we want the, cos is adjacent over hypotenuse, so we want the adjacent to be 1. So we're talking about that angle. So we know that cos to the minus 1 of a half is pi on 3. So x is equal to pi on 3. Well, where's our next solution? So our next solution will be, where's cos positive? So cos is positive in the first and fourth. So in the fourth we use 2 pi minus pi on 3, which is 5 pi on 3. And then we could get our next lot of solutions by adding 2 pi to each term or taking away 2 pi. So it will always be like a multiple of 2 pi. So the way we write that solution is we write x equals pi on 3 plus 2k pi, where k is an element of z. It's got to be a whole number because we want a whole multiple number of 2 pi. Or we could have x is equal to 5 pi on 3 plus 2k pi. Don't know why that just rubbed out. That was minus 2 pi. Okay, so if we put that on a common denominator, you could say that that's on 3. Take out pi as a common factor, and you'll have 1 plus, well, if it was 2k times 3 would have made it 6k, so it'd be 1 plus 6k pi on 3. Or do the same with the other one. X is equal to pi by 5 plus 6k on 3. Now, one thing to note is when you do cos, think about if k had been equal to minus 1 for the second one. So you'd have 5 minus 6 is minus pi on 3. Well, that would be like, you could write this like this. You could actually write plus or minus pi on 3 by 1 plus 6k. And that would be a nice, neat way to write all the solutions in one go. All right, that was A. B, we'll do the same thing. Root 3 tan 3x equals 1. So tan 3x equals 1 on root 3. So 3x equals tan to the minus 1 of 1 on root 3. Again, that's a special triangle, so we want the opposite to be 1 and the adjacent root 3. So that means if the opposite's 1, we're talking about that angle, which is pi on 6. So 3x equals pi on 6 plus 2k pi, because you could go around the unit circle any number of times you wanted, or 3x equals, so where else is tan positive? That's the third quadrant, so we use pi plus theta, so pi plus pi on 6 is 7 pi on 6 plus 2k pi. If you put that on a common denominator, that'll be pi by 1 plus 2k, 1 plus, putting it on 6, you'll have 12, yeah, so 1 plus 12k on 6, or 3x is equal to 7 plus 12k on 6 with a pi out the front, and then divide by the 3. So x equals, so if 3 goes to the bottom, that'll make that pi on 18. It's probably the nicest way to write it, as 1 plus 12k, or x is equal to pi on 18 by 7 plus 12k. I won't bother doing c because it's very similar. If I scroll down a little bit though, you'll see when they do it on the calculator, the way they write it slightly differently. And you get this, when you solve the equation for a general solution, you get this little n1. Well, this n1 is k. Now, sometimes it'll be n1, sometimes it'll be n2, sometimes it'll be n3. If you've solved something before with a constant, the next time it would make the constant n2, and then the next time n3, and so forth. So when you do your solve, x equals 6k minus 1 on 3. Now notice they put the pi at the end. I think when I did mine, I put mine, I did mine at the beginning. So that's their first one, and that's one of them, and then their other one is, or x equals 6k plus 1 on 3 by pi. So there's often more than one form you can get, but if you substitute in a value of k, you'll get the other form. So if you look at mine, I've got 5 plus 6k on 3. Well, how is that the same as 6k minus 1 pi? Well, what if k was equal to minus 1? Okay, so if k was equal to minus 1, my answer for the second one would become minus pi on 3. If k is equal to 0 for their answer, you see you still get minus pi on 3. So they're not wrong, they're just very fractionally different. They're written slightly different depending on where you start your k value from. So if you're ever in doubt, just check with a couple of different k values and you should get the same result. All right, I'll leave you to do the questions.